CO2, is that an acid or base? Well, you would say it's neither. It's neither an acid. Acid's supposed to have H, right? There's no H plus. It's not a base because this is not going to take hydroxide. That's because normally when you think about acids and bases, you think in terms of Bronsted. But this is not a Bronsted. This is Lewis. When we think in terms of Lewis, we're looking for electron pair donor, electron pair acceptor. Electron pair donor would be, well, there are electron pairs here. And so what makes a good electron pair donor? We want negative charge density, 1. And so when we do this, we see that the oxygens are delta minus, this is delta plus, delta minus, because these bonds are polar covalent bonds, right? And so this is, and so if this is delta minus and it has a lone pair, then we call these Lewis bases here. So that's a Lewis base. And so we have these two. These are both Lewis base sites. And this carbon here, this carbon's positive. So positive means it's more likely to accept electron density because electron density is negative. And so this would be a Lewis acid. But the problem is this already has an octet. It doesn't want another electron pair because can carbon expand its octet and have another electron pair added? No, carbon's incapable of that. But if we rearrange the electrons, it can. And so we have some choices. Now with water, water is the same thing. You know the hydrogens are delta plus. Let's make it blue. So delta plus. And so that means these hydrogens are acid sites. And this is delta minus, this is a base site, and it has lone pairs. It's base. And so we have two scenarios. The acid here on water reacts to the base. And in the jargon of Lewis acid-base reactivity, we always say base attacks the acid. And so this base here attacks this acid. One way of visualizing that is, I like to hybridize the terminals. Did you guys hybridize the terminals? What's the hybridization on carbon? What's the hybridization on oxygen? Did you hybridize or not hybridize? sp2. I hybridize. This is sp2. So I have an sp2 lone pair. This is sp2 orbital. This sp2 orbital gets pushed. We're going to think in terms of valence bond theory. Valence bond theory is easy. Is valence bond treats a bond as being the what? In valence bond theory, a bond is formed by the overlap of atomic orbitals. And so this bond here is an s orbital overlapping an sp3. So this is an s-sp3 sigma bond. And so if we have this sp2 push into this s orbital, it might kick these electrons out into the sp3 if we want to visualize it in terms of bond. And so this is how a Lewis acid-base reaction would proceed. It would proceed by this. This lone pair gets pushed into the s, it kicks these out into the sp3. That's one possibility. This is possibility 1. The other possibility is this. Possibility 2 is this sp3 lone pair here gets pushed. Well, there's no orbital here. And so it's going to get pushed here, but this is sp, and then there's p orbitals. There's pp pi bond here, pp pi bond here, and it gets pushed into the p, let's say, and then kicks these electrons out. This is possibility 2. That way we can maintain an octet. Otherwise, we would have too many. I'm going to tell you, either way happens because these collisions are just random collisions. It can collide. This oxygen can collide with this hydrogen, or this oxygen can collide with the carbon. Both are going to happen, but not both are going to lead to reaction. And I already know which one leads to reaction. What you do is, this is like the path through the jungle. Sometimes you'll just take all the paths and see where it takes you, right? This is what we do here. We take both paths to see where it takes us, but I don't have enough time to take both paths. So I'm just going to take the correct path. The correct path is going to be path 2, because that's going to lead to reaction. And so if we take path 2, we would get to this. We're going to have this carbon here. Now this carbon is going to be bonded to this water. That lone pair on the water is going to be now attached there, and then we're going to have a hydrogen sticking out here, hydrogen sticking out, and one lone pair like this. And then now this double bond is converted into single bond, and we're going to have 3 lone pairs on that, and then we'll still have a double bond over here, like that. How does this Lewis structure look to you? Does that look like a good Lewis structure to you? Yeah? Does everything have an octet? Octet rules satisfy? Octet rules satisfy. So this structure is good, right? Or does it look off? It looks off. What's wrong? What's less stable about this? This isn't as stable as that because what? Because of the oxygen, yeah. Because of the, what we call when you do Lewis structures, you look for octet and duets, and you look for one more thing. What else do you look for?
Symmetry.
Not always symmetry. Symmetry, maybe, maybe not. Formal charge. You look for formal charge. Formal charge. The formal charge is a little screwed up. The formal charge on this oxygen is what? +1. The formal charge on this oxygen? -1. And so basically all the other formal charges are 0. And so this formal charge +1, this is like oxygen. One oxygen wins, the other oxygen loses an electron in this structure. Is that stable? No, so this isn't as stable as that. The formal charges are there. And so one way to get rid of the formal charges is like this. This is what we call a Lewis acid-base reaction between two molecules, two different molecules. This would be a intermolecular reaction, inter. We can also have something called intramolecular reaction. Do you know what intra means versus inter? Inter means between, intra means within. And so we can have an intramolecular reaction. Well, we do. You know what this is? This is a pretty good Lewis base. Because not only does it doesn't have a delta minus, it has a full negative charge. This is full negative charge means this is good, pretty good base. And then look what's close by. What's that? It's a Lewis acid. Well, we gotta have a Lewis acid-base reaction. So let's say this sp3 lone pair here. This sp3 lone pair gets pushed into the s orbital because of vibrations. Are these molecules static or are they moving? They're moving. There's kinetic energy. The kinetic energy is, there's 3 types of kinetic energy. What are they? What are the 3 types of motion? Static would be no motion. Translational motion, rotational motion, and one more. Translational, rotational, and vibrational. And so what happens is we get a vibration. This vibration pushes this sp3 into the s, kicks out these. This was an ssp3, and it kicks that out into the sp3 orbital on oxygen. And so if we do that, then we end up with this. We end up with this. Do you recognize this? Do you know the name of this? The name of this is H2CO3, which is called carbonic acid. And so what happens is this. Is this very favorable? Not that favorable. I mean, there's really not much driving force for this. But you can't stop the collisions. Can you stop the water molecules from colliding with one another? No, you can't. You can't say stop colliding, right? And the same thing here. You can't stop CO2 from colliding with water. If CO2 collides with water, there's a chance of forming carbonic acid. This is why, do you know what the pH of our DI water is? DI stands for what? Deionized water. The pH of our deionized water is 4.5. Is that pure water? No. The reason why our deionized water has a pH of 4.5 is because it's stored in a tank, and the tank is filled with air. The air contains CO2. The CO2 collides with the water, and it forms a little bit of carbonic acid. Carbonic acid is not stable. It doesn't last, it'll decompose, but you can't stop the collisions. So even if it decomposes, a little bit more will form. And when we say, what we see is a little bit, well, that little bit can change the pH of the water. This is much more favored in the reverse, than the forward. But just because it's favored in the reverse means the forward doesn't occur. A little bit of the forward can't occur. A little bit of the forward does occur. Just a little bit. This is what we call an equilibrium. In Chem 1B, what our goal is to figure out how much carbonic acid forms. Can you tell me how much carbonic acid forms? Well, it depends on the pressure. Well, let's go with standard pressure. What is standard pressure? 1 atmosphere or 1 bar. And then let's figure out how much carbonic acid forms. It's a little bit, but we want to know how much. Well, in order to know how much, we need to know about driving forces. In order to know about driving forces, we need to know thermodynamics pretty well. And so this is kind of what we're doing in Chem 1B. We're going to spend a lot of time talking about equilibrium. Equilibrium is this. We have this fight between products and reactants. Which side wins and by how much? That's equilibrium in a chemical reaction. This is why I start with chemical reactions in Chem 1B, because we're interested in equilibrium, not like some of the equilibrium systems you've seen. The equilibrium systems you've seen are vapor pressure, solubility with saturated solutions, etc. Well, we're interested in equilibrium between the products and the reactants in a chemical reaction. And so that's what we're going to be looking at, because so far in Chem 1A, all you've said in stoichiometry is the reaction either goes, and if it goes 100%. We get the theoretical yield, right? We can calculate the percent yield. We get the limiting reagent. We always assume 100% reaction, or it doesn't go. There's 0 reaction. But in reality, sometimes we get cases like this. In reality, there's going to be collisions. The collisions, it's going to happen, and it's going to happen to a small extent. We want to know that little bit that happens, or the lot that happens. We want to figure out what happens in these. And so that's the whole idea behind Chem 1B, and this is why we spend so much time looking at equilibrium in Chem 1B. But before we do equilibrium, before we get into these, we want to know what we expect. Do we expect it to be CO2 and water mainly, or do we expect it to be mainly carbonic acid? And so before we do this calculation, we want to kind of predict what's going to happen in our head. In order to predict what's going to happen in our head, then we need to know this Chem 1A style reaction stuff. And we predict that which side's more favored, CO2 and water or carbonic acid? CO2 and water. CO2 and water is much more favored. Carbonic acid is unstable. In fact, in your equation, when I'm asking you to write the complete equation, the ionic equation, and net ionic equation, I don't want to see carbonic acid. I do not want to see carbonic acid, because can I go to the store and buy a bottle of carbonic acid? No, so I don't want to see carbonic acid, because if you're telling me carbonic acid is a product, then I want to package that product and sell it, because nobody sells carbonic acid, right? What I want to see is what I can actually get, and I can't actually get the carbonic acid, so I don't ever want to see carbonic acid in the CE, IE, and NIE. Well, some people said, oh, well, I wrote it in the first equation, but I didn't write it in the second. Well, I don't care, because each equation needs to stand alone, right? And so I don't want to see that. And so this is an example of a Lewis acid-base reaction. In this case, CO2 is what we call a Lewis acid. CO2 is a well-known Lewis acid in biology. In biology, if you don't exhale enough CO2, then your blood pH goes way down, just like our DI water. And you get into this condition called acidosis. When people hyperventilate or do something like that, the CO2, when you exhale that CO2, that's important in maintaining blood pH balance. CO2 is an acid. Here's an acid. It's being attacked by the base. And in this case, water is the Lewis base. Anyway, I kind of went through it quick, but we're going to hit some of the points that I skipped. Actually, I hit all the points in Chem 1A, but I don't know. Did you guys cover much reactions in Chem 1A? Was this pretty? Okay, that's good. screen. All right. So what we're going to do next is I want to check off. I want to make sure everybody does that metathesis reaction correct. And then once you do that metathesis reaction, we're going to move on to a redox reaction I want you to do. So these are the reactions I want you to do, and I'm going to check these off as you do them. And so the first reaction was the calcium carbonate. Plus sulfuric acid. And once that's completely checked off, then I'll make a note of it. This is the second reaction I'm going to ask you to do is silver and nitric acid. And then the third reaction I'm going to ask you to do is sodium. What did I do? Actually, I got to look at my PowerPoint. Sodium monohydrogen phosphate. Plus potassium hydrogen sulfate. We'll do these three. I'm going to make these worth points once you get it complete. This is going to be. We'll just do this as this will be simple. This is 1 point. This is 1 point. This is 1 point. 3 points total. Okay. You'll have to have these completed. Let's try to get these done by certain time. Okay. You could work with your neighbor or your friends. This is an open book, open notes. You could work with whatever resources you want, but get them done today, quickly. And then we got to continue with chapter 24 and chapter 13 start.